Let's begin today's class with a quick review about the cross product or vector product. So when you see the cross product written, it's written this way. So vector C is the cross product of vector A and vector B. So it's not like we actually use that as a formula to calculate the cross product. What we do is we say the magnitude of the cross product is the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. Okay, so again, if this is vector A and this is vector B, then the angle we're talking about is this angle. And the magnitude of the new vector C is just going to be the length of A, the length of B, times the sine of the angle between them. Remember, when we say magnitudes, we mean always positive. It's literally just the lengths of the vectors. Okay, so vector C is obviously a vector, so it has a direction. Remember that we use the right-hand rule to find that direction. Now, it's actually simpler than it first seems, because the key thing to remember is that the resultant vector, vector C, is perpendicular to both of the original vectors. So that means that vector A and vector B form a plane, and vector C is perpendicular to that plane. So when I draw these two vectors, which are in the plane of the screen, notice that the only two possible choices for the direction of vector C is either directly out or directly in. Okay? And remember that we use a dot with a circle around it to mean a vector that's coming out, and a circle with an X in it to mean a vector that's going in. And you're supposed to picture either an arrow coming towards you or away from you. That's how you're supposed to remember that. Okay, so how do we do it? We put our first finger in the direction of A. Now, without changing the direction of your first finger, rotate your hand until you can get your second finger pointing in the direction of B. What you should see is that your thumb is coming towards you. In other words, vector C is out. So remember that vector A and vector B form a plane. Vector C is perpendicular to that plane. In other words, perpendicular to the original two vectors. So then we talked about how this pertains to the force on a charged particle in a magnetic field. The first thing to remember about this force is that if the charge isn't moving, there is no force. Notice that it depends on the velocity of the charge. Also notice it's a cross product, V cross B. So V is the first vector, so that's where your first finger goes. B is the second vector, so that's where your second finger goes. And then again, the force is your thumb. Once again, vector V and B together determine a plane. The force has to be perpendicular to both the original two vectors. So if I tell you that the velocity of the particle is in that direction, and vector B, the magnetic field, is in that direction, go ahead and see if you can figure out the direction of the force. So first finger in the direction of V, rotate your hand so you keep that first finger pointing to V, and your second finger can now point in the direction of B. You should find that your thumb is pointing towards the screen. In other words, the force is in. Now, again, we don't use this as a formula to actually calculate the force. What we do is we find the magnitude. And so the magnitude of the force is QVB sine theta. Again, theta is the angle between V and B. Also, remember that if the particle is negative, you either have to flip your answer that you get with a right-hand rule or simply use your left hand. Let's look at another example that requires us to use the right-hand rule. Remember that last time we looked at the motion of an electron in a magnetic field. Here we're going to look at something different. We've got a beam of protons. It's entering a region that contains both an electric field and a magnetic field. The strength of the electric field is 5,000 volts per meter, What is the magnitude and the direction of the magnetic field required to keep the protons moving in a straight line? Okay, so first let's look at this conceptually. We've got our particles. We want them to go through in a straight line. However, notice that in this region between the plates, notice that this is the positive plate up here, and this is the negative plate down here, just based on the direction of the field. You'll notice that for our proton, the force of the electric field is straight down. Remember, the electric force is simple. It's just in the direction of the electric field, or opposite for a negative particle. Okay, so the electric field is exerting a force straight down on the proton in that region of space. If we want the proton to go straight through, then clearly we need the magnetic force to be up. So now the question is, what magnetic field direction would give us that? So take your right hand, and again, make sure you use your right hand. It's very typical for right-handed people to not put their pencil down and use their left hand by mistake. Don't make that mistake. Okay, so here this is a little trickier. I want you to put your first finger in the direction that the protons are going. Now orient your hand so that your thumb points in the direction that we figured out the force of the magnetic field has to be. And now figure out, where is your second finger pointing? You should see that it's pointing into the screen. So B is in. And again, that's the symbol we use. Now, to solve the problem numerically, all we have to do is we figured out what direction B is so that the forces are opposite each other. And now we just have to make sure that the magnitudes of the forces are the same so that they will perfectly cancel out. So how do we do that? Well, again, we want to do FE is equal to FB. Remember, we know what the force is due to the electric field. It's just the magnitude is Q times E. We know the magnitude of the force due to the magnetic field is Q VB sine theta. And remember, we figured out that B in this region of space was in. So we said B was in. And therefore, if B is straight in and V is to the right, the angle between V and B is 90 degrees. Okay, so notice we can cancel out the charge on each side, and the sine of 90 is going to be 1. And what we get is that V is equal to E divided by B. Now, in the problem, we're asked to find the magnetic field, and we can do that in a second. But this device that we've just been looking at is called a velocity selector. And I want to just make sure you understand why it's called that. Notice that what we did was we said, if we want this velocity particle to go straight through, then we need to make sure that the electric force and the magnetic force perfectly balance off. And so that's what we solved for. But now think about what happens if you send a particle going through too fast. Well, remember, the magnetic force depends on the velocity, but the electrical force does not. And so a particle that's going too fast will experience a greater magnetic force and will be deflected up. So that would be a particle going too fast. On the other hand, a particle that's going too slow, now the magnetic force would be less, but again, the electrical force wouldn't change. So a particle that's going too slow would end up down here. And so only the particles that are going at the particular speed we want will go straight through. And we now have a way to get electrons or protons, whatever particle we want, to make sure we just have the speed that we want for those particles. So it's called a velocity selector for that reason. Okay, to finish off the problem, the magnetic field is what we're looking for, so that would be E divided by V, or 5,000 volts per meter. divided by 4.8 times 10 to the 5th meters per second. And if we work that out, we get that the magnetic field is 1.0 times 10 to the minus 2. And remember, our unit of magnetic field is the Tesla. Okay, let's look at another important rule that we need to understand, and that is the force on a current-carrying wire in a magnetic field. Now, this actually just comes from the fact that if individual charges experience a force QV cross B, then obviously if I have a wire that has a current in it, well, a current is just moving charges. So that whole wire is going to experience a force. So instead of the velocity and the charge, we have the current, and L is the length of the wire that's in the magnetic field in the direction of the current. Okay? So here we have a section of wire that is placed in a magnetic field, and we can find the direction of the force by using our regular cross product rule. So this vector L is just the length of the wire in the direction of the current. So if the current is going this way in the wire, here is vector L. And remember, the first vector in the cross product is your first finger. The second vector in the cross product is your second finger. So why don't you go ahead, put your first finger in the direction of L, orient your hand so that your first finger can still point in the direction of L, but your second finger can now point in the direction of B, and look at where your thumb is pointing. Remember, you're only trying to differentiate between in and out. You should see that your thumb is pointing out. So the force, in this case, is out. And again, remember, that's our symbol for recording that. Now, how do we find the magnitude of that force? Well, the way we always do with a cross product, it's just the magnitude of the two vectors. If there's something in front, it gets multiplied as well, and we get the sine of theta. So the magnitude when you have a current-carrying wire, the magnitude of the force on that wire in a magnetic field is just ILB sine theta. And again, what is theta? It's the angle between B and L. So let's just do a little bit of practice with the right-hand rule. It says there's a uniform magnetic field pointing out of the paper. So everywhere on the paper is a magnetic field that's pointing out. And I've just drawn some segments of wires. Obviously, you normally need a complete circuit, but we're just drawing pieces of wire here for the purpose of practicing. So why don't you go ahead and look at what is the force on this wire where the current is straight down, on this wire where it's to the side, and this wire where it's coming right at you. All right, so pause the video and see if you can work those out on your own. All right, well, let's look at this one first. We put our first finger in the direction of I. Rotate your hand so that your first finger is still in the direction of I, your second finger is pointing straight out, and look at where your thumb is pointing. It should be pointing down like this. So that would be the correct direction for the force. For this wire, again, first finger straight down, second finger pointing straight at you. You should see that your thumb is pointing this way. Finally, for this one, if you put your first finger in the direction of the current and now try to keep it that way and your second finger also in the direction of the current, you notice it doesn't look right. They're both pointing in the same direction. Well, that's because the answer here is no force. Because notice that when you have F equals ILB sine theta, that if theta is 0, which it is in this case, or if it's 180, then that's going to be a magnitude of 0. Remember that for a charge in a magnetic field as well. If the velocity and the magnetic field are in the same direction, or directly opposite, there is no force on the charge. Okay, here's a problem for you. Why don't you go ahead and pause the video and figure out both the magnitude of the magnetic field in this case and the force, the direction of the force. Okay, so hopefully you were able to figure this one out. For the formula, we know that the magnitude of the force is ILB sine theta. So that's what we're going to be working with. In this particular problem, you'll notice we were given the length of the wire in the field, the current, the angle, and we were given the force, and we're asked to find the strength of the field. So in other words, we're solving for B. So let's go ahead and just first solve that algebraically. For B, we get B is equal to F divided by IL sine theta. And therefore, we've got a force of 5 newtons. We're dividing by a current of 3 amps, a length of 0.5 meters, and a sine of 30 degrees. So as long as you got your calculator in the right mode and you don't fat finger something, you should have gotten 6.7 Teslas for your answer. Now, in terms of the direction of the force, again, put your first finger in the direction of the current. Do not change that. All you're allowed to do now is rotate your hand so that your second finger can point in the direction of B and your first finger is still in the direction of I. You should find that the force is in. Again, remember, since both I and B are in the plane of the screen, the only two possible choices were in or out. Okay, I want to just remind you of how we figure out the electric field due to a distribution of charge. We basically have two ways to do it. We can either use Gauss's law, and we spent lots of time working on Gauss's law, but we saw that Gauss's law only helps us when we have very symmetrical situations. What if instead we've got just like some blob of charge here, blob of charge Q, and I want to know what is the electric field at some point in space, a distance r from this blob. Well, what you'd have to actually do to figure that out is you'd have to look at a little bit of charge, dq, and say, well, what is the electric field that that little amount of charge creates at this point, which we call dE. And then what you do is effectively you would have to add up all the little bits of charge that make up that object dq and all of the little bits of electric field they create. So in other words, every little bit of charge just creates the electric field of a point charge, right? kq over r squared or k dq over r squared. And then you'd simply have to add up all the little pieces that make up the object, okay? So we didn't do any problems where we actually integrated things like that, but conceptually I want to make sure you understand that that's how you could do it. It's just like adding up many electric fields due to many point charges. Well, it turns out that there's a similar way that we can do this for magnetism. It's called the Biot-Savart law, and we're actually not going to do these integrals, but I want you again to conceptually understand what you would do. So really the equivalent of a charge creating an electric field, we've said for magnetism, is that it's moving charges that create magnetic fields. So we can think of that as little bits of current. So if I've got a wire here creating a current, I can think of a little piece of the wire creating a magnetic field at this point. And if I could break this wire into little pieces, each creating little bits of magnetic field at this point, if I could add all of that up, that would give me the magnetic field due to that current carrying wire. Okay? So the reason I'm not going to have you guys do this type of integral is it's really more of an exercise in integration than physics. And I want to concentrate at this point in the course on more of the conceptual understanding. So for example, moving charges or currents create magnetic fields. That's the key thing I want you to remember. And the bios of art law is just the mechanics of how you could figure that out. Now we're going to find there's some other ways to do it that we are going to do. We'll get to that in a minute. But first what I want to do is I want to just actually tell you what is the magnetic field created by a long straight wire. In the textbook you can read through how to actually do that with a bios of art law, but I'm just going to give you the result. The magnetic field of a current carrying wire is mu naught I over 2 pi r. Remember that mu naught is our constant for magnetism that is related to epsilon naught. So in other words, epsilon naught is the permittivity of free space that we learned about back when we covered Gauss's law. Mu naught is the magnetic equivalent. We call it the permeability of free space. And again, it's the fundamental constant of magnetism, just like epsilon naught is the fundamental constant of electricity. So what is this formula telling us? It's telling us that if we are a certain distance r from the wire, the magnetic field at that point in space is given by this formula. Now you'll notice in the diagram that it's showing these blue circles around the wire. What that's showing you is that the magnetic field, in terms of its direction, is always in a direction tangent to a circle around the wire. So this gives you the value, but the direction is always tangent to the circle around the wire. And so in order for us to remember that, we're going to introduce right-hand rule number 2. So right-hand rule number 2 says if you want to figure out what is the direction of the magnetic field created by a current carrying wire, put your thumb in the direction of the current, and then your fingers will show you the direction that the magnetic field goes around the wire. Okay? So notice how your fingers curl around the wire in the direction of the magnetic field. Okay? So that's right-hand rule number 2. Put your thumb in the direction of the current, your fingers show you how the magnetic field curls around the wire. So let's look at a couple examples of this. The first one is, what's the direction of the magnetic field line surrounding a wire carrying current straight out of the board? So imagine there's a current coming straight out at you. Well, what we've just said is that the magnetic field around a wire the magnetic field lines are circular, and I should draw them as being farther and farther apart as I go out, because we've seen that the strength decreases as I move away from the wire. Okay, so again, the strength of the magnetic field is mu naught I over 2 pi r naught, where, sorry, not r naught, 2 pi r, where r is the distance I am away. But in terms of the direction of these field lines, put your thumb so it's coming straight at you, because that's the direction of the current. Notice that your fingers are now curling counterclockwise. And so the direction of those magnetic field lines would be like that. They would be counterclockwise. Let's take a look at another question. It says, what is the direction of the magnetic field to the right and to the left of the wire in the plane of the board, or the plane of the screen? So here, what I want you to do is put your thumb in the direction of the current, and notice that if your fingers are to the left of the screen, notice that they're pointing in, they're hitting the screen. But if you hold your thumb, again pointing down, and now have your fingers to the right, notice that your fingers are coming out of the screen. And so really what you're picturing here are these circular field lines, but we're picturing them just in the plane of the board. So on the left-hand side, they go in, and on the right-hand side, they go out. So that's important that you can see that in 2 dimensions. Okay, so again, thumb in the direction of the current. Notice your fingers point in if they're on the left. If you orient your hand so that your fingers are to the right of your thumb, they point out. Okay, so what we want to look at now is the force that exists between 2 current-carrying wires. If you take 2 wires and you put a current in each one of them, we're going to see that they affect each other with a magnetic force. And I want to first look at what is the equivalent problem that we've already covered from electricity. So here's the equivalent problem from electricity. And that is simply, I've got charge 1 and I got charge 2. And I want to know what is the force that charge 1 exerts on charge 2. Now, the first time we looked at this, we used Coulomb's law. But remember, then we changed the whole way that we look at this. And this is so important to make sure you get this. Hopefully you already have this, but if not, that you have it for the final, because I'm going to ask you conceptual questions like this on the final. Remember that the way charge 1 exerts a force on charge 2 is charge 1 creates an electric field. And then we say charge 2 experiences a force in that field. Okay? And obviously you can look at it the other way. Charge 2 creates an electric field. Charge 1 experiences a force in that field. But that's really important to remember that. So the reason that charge 1 exerts a force F12 on charge 2 is because it creates an electric field, right? So it would create an electric field at charge 2 of KQ1 over R squared, where R is how far away we are. Right? That's the electric field that charge 1 is creating at that point. And now charge 2 experiences a force just from F equals QE, right? Charge 2 in that electric field. Now, of course, if you take E1 and stick it in there, then what you find is that the force that 1 exerts on 2 is K Q1 Q2 over R squared. We get back to Coulomb's law. Okay, so what was the point of that review? To remind you that the reason that charge 2 experiences a force is charge 1 creates an electric field. Charge 2 experiences a force because it's now in that electric field. So here's how it's relevant for this problem that we're going to do. Wire number 1, which has a current in it, we know that a current carrying wire creates a magnetic field. We also know that if you take a current carrying wire and place it in a magnetic field, it experiences a force. So hopefully you'll see that this problem is the direct magnetic analogy of that problem. Okay, so let's go ahead and solve the new problem. So here are the 2 formulas that we've covered so far today. We've said that if you have a wire in a magnetic field, it experiences a force. It's a cross product, but that's the magnitude of the force. We've also said that a wire creates a magnetic field given by that formula. So let's figure out the force on wire number 2. So the force that wire 1 exerts on wire 2. That's what we want to find. Well, the first thing that we're going to do is we're going to conceptualize the fact that wire 1 is creating a magnetic field. So wire number 1 is creating a magnetic field, which I'm going to call B1, which is mu naught I 1 over 2 pi. And instead of R, since I've got where I want to know the strength of the magnetic field created by wire 1 is right over here where wire 2 is. Notice it's a distance d away. Okay, so that's the magnetic field that wire number 1 is creating over here, right? So now we know that wire 2 is in a magnetic field. Well, what's the force on it? It's just from this formula, the force on wire number 2 is going to be the current in wire number 2 times whatever the length of the wire is in the field, so we'll just call this L, times the strength of the field it's in. But what field is it in? It's in the field created by wire number 1. So mu naught I1 over 2 pi times d, and then times the angle. So now we got to think about the angle. Well, what is the direction of the magnetic field created by wire number 1 over here? So I put my thumb in the direction of wire number 1, and I see that my fingers are pointing in over here. So the magnetic field created by wire number 1 is in. So now I'm going to do my right-hand rule of my first finger in the direction of the current, orient my hand so my second finger can point in the direction of the magnetic field, and hopefully you can see that the force F12 is in that direction. And so the angle, by the way, is just 90 degrees. Because the angle we're talking about there is between B, which is straight in, and I, which is straight up. Okay, so what we get, if I take that now and rewrite it, is I get F12 is equal to mu naught I1 I2 times L over 2 pi d. And often the way we write this is we write it as a force per length. And so we get mu naught I1 I2 over 2 pi times d. What I want you to notice is that is effectively the equivalent of Coulomb's law in magnetism. Notice instead of the charges, we have the currents. Instead of our constant k, we got mu naught. And then we've got the distance between the wires as opposed to the distance between the charges. Notice, by the way, if F12 is to the left, then F21 has to be to the right, just because of Newton's third law. But try to work it out. In other words, the direction of the magnetic field created by wire 2 over here would be out. That would be B2. It's got to work both ways. If you look at, put your finger in the direction of I1, orient your second finger so that it's coming straight out at you, you should see that your thumb points to the right. Let's look at how this changes if one of the currents is up and one of the currents is down. So this is really important to be able to work this out. Again, if I'm trying to find the force on wire number 2, I want to first figure out what is the direction of the magnetic field created by wire 1 over there. So thumb in the direction of the current, look at where my fingers are, and what I see is that the magnetic field is in due to wire 1, where wire number 2 is. So now I use my right-hand rule that I put my first finger in the direction of the current, orient my hand so that my second finger can point in, and I'll notice that my thumb is pointing to the right. So notice that now the wires are repelling each other. Again, go through on your own that the magnetic field that wire number 2 creates is also in here. And since the current is up, the force on that wire would be to the left. Okay. Let's look at the magnetic field created by a loop of wire. So what I want you to do here is, let's say that our current is going clockwise. So take your thumb and put it in the direction of the loop and try to figure out what is the direction of the magnetic field going into the or inside the loop, and what is the direction of the magnetic field outside the loop. So notice that if your thumb is going along the loop and your fingers are outside the loop, they're pointing out towards you. But notice that if you have your thumb in the direction of the current and your fingers are inside the loop, they're actually pointing in. And so the magnetic field everywhere inside the loop would be in, and everywhere outside the loop would be out. Here's kind of a quasi three-dimensional picture that sort of shows you that. Now, it turns out that in the next chapter, loops are going to be really important. And so we want a quick way to figure out the direction of the magnetic field inside a loop. And so the way we do that is what we call right-hand rule number 3. And that is, we now flip what we do with our fingers and our thumbs. So let's say that we've got a current that's going this way in this wire. So take your fingers and curl them in the direction of the current, and then notice where your thumb is pointing. If your thumb is pointing out, as it should be, then we know the direction of the magnetic field anywhere inside that loop is out. If instead the current is going clockwise, notice that now you find that the direction of the magnetic field anywhere inside the loop is in. Notice this version of the right-hand rule only works to tell you the direction of the magnetic field inside the loop. And again, this rule is going to be really important in our next chapter.